All right, this section is on prime numbers and prime polynomials. So the beginning on prime numbers should be pretty familiar to you. And we'll start with the definition of a prime number, which is an integer n is prime if and only if, first of all, n has to be greater than 1. So 1 is not a prime number technically by the definition of prime. And the numbers 1 and n are the only positive factors of n. Positive integer factors. Sorry, not enough room here. Factors of n. So for example, 3 examples of numbers that are prime. 2 is prime. It's the only even prime number. The only factors of 2 are 1 and 2. So by definition of prime, 2 is prime. 3 is prime. The only factors of 3 are 1 and 3. 29 is prime. So obviously I skipped a few, but just giving those examples again, the only factors of 29 are 1 and 29. So 3 examples of numbers that are not prime would be any number that has factors other than 1 in itself. For example, 4 has 4 and 1, but it also has 2 and 2. 6 has 6 and 1, but it also has 2 and 3, so on and so forth. So there are many of these types of numbers. If a number is not prime, that's called a composite number. So all of these are composite numbers because they're composed of factors other than just 1 and itself. And the prime factor theorem says that every integer greater than 1 is either prime, and if it's not prime, obviously it's composite, but if it is composite, then it has a prime factor. So every integer greater than 1 is either prime or it has a prime factor. For example, 10. It's not prime, but it does have a prime factor of 2 and 5. So every number can be described in that way, either prime or contains prime factors. The infinitude of primes theorem, I know there's a bunch of boxes and words on this page. Really, it's just getting through some formal information that we need to get through, and then we'll get to some examples. But the infinitude of primes theorem just says that there are infinitely many prime numbers. So, infinitely, you'd think that once you get into the larger numbers towards infinity, larger and larger, that all of those numbers would have some factor other than 1 in itself. But in fact, there are infinitely many prime numbers, and computers are still generating larger and larger prime numbers. Okay, the factor search theorem right here is actually pretty cool. And it says that if an integer n, so n is a number, if it has no prime factors between 1 and its own square root, the square root of n, including the square root of n and 1, then it is a prime number. So if you're checking, and we'll see some examples in a minute, but if you're checking to see if something is a prime number, for example, say 129, I want to know if 129 is a prime number. Instead of checking, can I divide 129 by all of the numbers between 1 and 129, all I have to really check are all of the numbers between 1 and the square root of 129. So that narrows down a smaller set of numbers to check to see if they're factors of 129. And if not, if none of those numbers between 1 and the square root of 129 are factors of 129, then it is in fact prime. And we'll do some examples in a minute so you can see what I mean by that. All right, the fundamental theorem of arithmetic is pretty simple. It's just making the statement that any number greater than 1 is either a prime number, it's either prime, and if it's not prime, then it has a prime factorization, so you can factor it. Factorization that is unique except for the order of the factors. And I'll show you what I mean, the order of the factors. So every number greater than 1 is either prime, and if it's not prime, then you can factor it into its prime factors, and that factorization is unique to that number, except for the order of the factors, and I'll show you in a couple examples on the next page. So first I want to show you guys how to use the factor search theorem. So the factor search theorem, again, right up here, says that if an integer has no prime factors between 1 and the square root of itself, then it is a prime number. So, for example, if you take example 1 here, 151, I want to see if 151 is a prime number. So A says, list the numbers that must be tested as factors to determine whether n is prime. So I need to test all of the numbers between 1 and the square root of 151. And then if none of those are factors of 151, then it's prime. Okay, so we take the square root first of 151. The square root of 151 is 12.28 ... So I need to check, all I need to check to see if 151 is prime is all of the prime numbers between 1 and 12.28. Obviously, just between 1 and 12. So those numbers would be 2, 3. So we're listing out all of those prime numbers. 5, 7, not 8, not 9, not 10, and 11. So each of these are prime numbers. These are the only prime numbers between 1 and the square root of 151. So if 151 is not divisible by any of these, then we have done enough to show that 151 is prime. So then you would just check and see if is 151 divisible by 2? Obviously not. Is it divisible by 3? No, I get a decimal. 151 divided by 5? Obviously not. 151 divided by 7 is a decimal, and 151 divided by 11 is also a decimal. So I've checked all of these. 151 is not divisible by any of those, so it has no prime factors, which means 151 is a prime number. So let's do this next one here. 1,147, is that a prime number? So we need to check all of the prime numbers between 1 and the square root of 1,147. So you would use your calculator, find the square root of 1,147, which is 33.86. So 33.8. So we need to check, we need to first list all of the numbers that we need to test. So we are testing values between 1 and 33. So only the prime numbers. So you have to think a little bit and go through one at a time, list out those prime numbers. So I want you to do that on your own right now. So pause the video, list out all of the numbers, prime numbers between 1 and 33. Okay, so you can see that I've listed out all of those prime numbers between 1 and the square root of 1147, which is 33.8 something. So this set of numbers here, all I have to do is see if 1147 is divisible by any of those to see if it's prime. So at this point, what you need to do, I would again ask you to pause the video, use your calculator, divide 147 by each of these numbers, and you're going to see are any of these a factor of 1147? And if any of these are a factor, then obviously it's not prime. So go ahead and take a second to do that. Okay, so if you took the time to do that, you would have gone through one at a time, and it looks like none of these are going to be factors of 1147 until you get to the last one, 31. So you end up finding that 1147 is in fact divisible by 31 because it's 31 times 37. So no, 1147 is not prime. So again, this is using the factor search theorem, which is a pretty cool, shorter way to figure out without testing a million different numbers if a number is prime or not. Okay, on the next page, we're going to sample that you should have seen many times before, just giving the prime factorization of a number. When you're writing the prime factorization of a number, you're breaking the number down using what you guys have probably done before, using factor trees to break it down bit by bit to see what are all of those prime factors. So every number that's not prime can be broken down into factors that are each prime. And those factors may have exponents, but they're all broken down into those factors and exponents of factors. So if we're breaking down 160, let's just start simple, and we know that that can be broken down into 16 times 10. And you could have done 4 times 40 or any other way you can break apart 160 into two factors. Then you're going to take each of those factors and continue breaking them down. So we know 16 is 4 times 4, and 10 is 5 times 2. Now 5 times 2, both of these are prime numbers, so those can't be broken down any further. So 5 and 2 are definitely two of the prime factors of 160. But 4 and 4 can still be broken down. So 4 can be broken down into 2 times 2, and this 4 can be broken down into 2 times 2. So once you get to that bottom level of every number is broken down into that smallest factor that's prime, you've broken down the number 160 is 2 times 2 times 2 times 2 times 5 times 2. So to represent 160 in its prime factorization, the typical rule is that you write the factors from least to greatest. So the smallest factor here, it only has two prime factors, 5 and 2. You list them in order of least to greatest, so 2, but it's 2 times 2 times 2 times 2 times 2. So 160 is actually 2 to the 5th times 5. So that's the prime factorization of 160. All right, so if we look at example B, it's a little more robust. So instead of a number simple like 160, we see a large number that we might not know some of the obvious, there might not be as many obvious factors of this number. To start breaking it down, I would look at the end of the number. If it ends in a 50, it's obviously divisible by 50. So I would go ahead and try that first. So we know that this number is going to be 50 times something else. So using your calculator, type in 221, 850 divided by 50. And the other factor is 4437. So I'm trying to break down each of these two numbers. So I know 50 I can break down into 5 and 10. 5 is prime, so I'm done right there. 10 can still be broken down into 5 times 2. Each of those are also prime. So I'm kind of halfway done on that left-hand side. I know 5 and 2 are 3 of the prime factors of our number. But now I still have the challenge of breaking down 4,437. So again, looking at that last number, 7, it's obviously not divisible by 2, it's not divisible by 5, it's not divisible by 10. So then you want to start trying some other numbers. I'm hoping by now you all know the trick that if you add up each of the digits, 4 plus 4 plus 3 plus 7. So when you do that, you get 8, 9, 10, 11 plus 7 is 18. 18 is the sum of these digits, and because 18 is divisible by 3, that means this whole number is also divisible by 3. So that's a quick trick to use. So we know that 4437 can be broken down into 3 times 1,479. So now I want to figure out, can I continue breaking that down? 3 obviously is going to be the end of that line right there, but I want to see if I can continue breaking this number down. I'm going to add up again and see if they're divisible by 3 first. I'd say that's the best way to start. So that would be 5 plus 7 is 12 plus 9 is 21. So this is, which is divisible by 3. So 1479 divided by 3 is 493. 493. Now I want to see, obviously 3 is done here, but I need to continue breaking down 493 if possible. So I don't know if that's divisible by anything else. I can add up these digits and I get 16. 4 plus 9 plus 3 is 16. 16 is not divisible by 3, so 493 is not divisible by 3, but I'm still not convinced that 493 is a prime number. So I'm going to use the factor search theorem, which means testing all of the numbers between 1 and the square root of 493, which is 22. So I need to test 2, 3, which we know neither of those will work, 5, 7, 11, 13, 14, 15, 16, 17, 19, and that's it. Those are all the prime numbers between 1 and 22. So then what I would do is test each of these one by one. So 493, obviously not divisible by 5. It's not divisible by 7. It's not divisible by 11. It's not divisible by 13. It is divisible by 17. So that's a good use that you just saw of the factor search theorem, because then you can be convinced if it's prime or not. So we found that it's 17 divided by 19. Both of those are prime numbers. So we can complete this by writing the final prime factorization of our number. So this number, we go through, first we list all of the prime factors, so underlined in green, from least to greatest. So I have 2 times 3 times 3, so that would be 3 squared. The next one is 5. I have 2 of those, so 5 squared, 17, and 19. So that is the prime factorization of our number, doing that step by step. So that's something that you guys have probably done. You may need to be able to do in a larger fashion now with larger numbers. The rest of this section is really just on prime polynomials, which when you're representing a prime polynomial or showing prime factorization, you're just factoring. So a lot of this is review. We're just going to be factoring polynomials. I'm not so much worried that you memorize definition of a prime, either of these things, but just be able to represent the factored form of a polynomial. So a polynomial p of x with degree greater than 1 is prime if and only if the only polynomial factors of the polynomial with real coefficients are constants or constant multiples of p of x. And then we have the unique factorization theorem for polynomials, which is similar to the factorization theorem for integers. So p of x is a polynomial. Either p of x is prime, or it has a prime factorization over the reals, which is unique except for the order of the factors or the multiplication by the coefficients. By real coefficients. So it's similar to, by real constants. So that just goes back to saying that you can factor any polynomial into its prime factorization. It's going to be unique, except for, just like these are unique, except for the order. So there could be other numbers with the order of 2 times 5, but their exponents will be different. So you'll see the same thing with polynomials. The only difference with these, when it says factor completely, so we're just factoring. It says give the prime factorization. It's just factoring, which we've done over and over. The only difference is that we're factoring over the set of real numbers. So that means we are going to be including square roots in our factors this time. So it's one extra step. So in an example like A, if you look at it, it's a quadratic. The coefficient of this is not 1. So what we would do is multiply these two numbers together and factor by grouping. So I'm looking for factors of 60 that add to 11. And that would be 15 and negative 4. So now I can split this into 6x squared plus 15x minus 4x minus 10. And then from there I can factor by grouping. So you all know how to do this. I would encourage you to pause the video, finish this factorization on your own just to stay on top of this process before moving on. Okay, so there's the prime factorization of A. B is a little different, so we've got this, our exponents are 4 and 2. So you can still treat that as a quadratic, but we're looking, instead of our first two terms of the quadratic being x times x, it's going to be x squared times x squared. Again, you have got, there's nothing we can factor out of each of these three terms. So the first thing I would do is multiply 12 times 20, and we're going to look for factors of 12, that product that add to negative 31. So you can pause and take a minute to try and figure this out on your own. So we're looking for, how can I break up 240 into two factors that add to negative 31. Both of them are going to be negative in order to do that. So I would encourage you to pause and try and figure that out right now. And those two factors are negative 15 and negative 16. So those multiply to positive 240, but when you add them together you get negative 31. So that means we can break this down into 20x to the fourth minus 15x squared minus 16x squared plus 12. From here we will factor by grouping. So we've got this group and this group. Out of my first group I can factor out 5x squared. That leaves me with 4x squared minus 3. Out of my second group we need to factor out a negative 4, and that leaves me with 4x squared plus 3, just what you wanted. So that we can complete our factorization, and that's 4x squared minus 3 times 5x squared minus 4. Now, this is completely factored over the integers. However, we are now factoring over the real numbers. So we're here, we would, at this point, we would say, okay, do I have any perfect squares or difference of squares? And it doesn't look like I do. But over the real numbers, we can still treat this as a difference of squares. And that difference of squares, I'll just remind you guys what difference of squares means. When you have, like, for example, x squared minus 4. That's x plus 2, x minus 2. So it's the same idea. Now these don't look like difference of squares. This is a perfect square. This is 2x squared. But 3 is not a perfect square, but we can still break it down. 3 is still the square root of 3 times the square root of 3. So we definitely can still break that down over the real numbers. So hang with me. It's a little uncomfortable to think of it in this way, but you'll see. Let me erase this. No, I can't erase that. Okay, so let's break this down. So 4x squared minus 3. I can break that down into a difference of squares by writing 2x plus the square root of 3 times 2x minus the square root of 3. So this comes from that minus 3. So if you think of 3 as the square of root 3, then you can still break it down. Same with the next one. So 5x squared is really the square of the square root of 5x. And then this minus 4 means I'll do plus 2. And then square root of 5x minus 2. So this extra step is just one last step when factoring over the real numbers. You need to pay attention to difference of squares, just difference of squares. So these numbers need to be subtracted in order to use this. Okay, let's see the difference of squares again to get a little more practice with that. So if we look at example C here, this one looks a little friendlier. We know that we can at least factor out a 2 from both of those terms to begin. So we have 2 times x to the 4th minus 4. From here, I'm hoping, like I just said, you guys recognize this definitely is a difference of squares that you should, that we would have factored as a difference of squares even before this section. So x to the 4th minus 4 is the difference of squares that can be factored into x squared plus 2, x squared minus 2. Now, this is the point where we would stop before this unit, before this section, because we're finished factoring over the integers. This is x squared plus 2. It's not a difference of squares because it's plus, and there's nothing I can do to continue factoring this over the real numbers. However, if you look at this, this is definitely a difference of squares because this is x squared and this is root 2 squared. So we can factor at one more level over the reals. So these first two factors stay the same. X squared minus 2 can be factored as difference of squares of x plus root 2 times x minus root 2. So we have that one extra step of factoring this difference as a difference of squares because we're not just factoring over the integers, at which point we would be done here. But since we're factoring over the reals, we need to take it one step further. So I'm going to stop here, but I just wanted to show you guys what that looks like when you take it one step further to factor over the reals. We're going to skip E. Typically I would do D in class. I'm just going to explain D, but I'm not going to, maybe I'll work through it, but I'm going to ask you to pause the video and work through it yourself. Initially, if you look at D, it's got 4 terms, and typically with a 4-term polynomial that we're factoring, we would factor by grouping. But if you look closely at D, there's no way to rearrange these or group these to where when you factor it, you have 2 groups with the same factors, because I could factor 2 out of both of these terms, but it's still not going to get me looking like x minus 15. So factoring by grouping won't work here. So to do this problem, if you remember from the last section, what we would do first then is actually graph this polynomial, look for an integer 0. So you would look for a 0 on the graph, and then find that integer that's a 0 and factor that factor out. So pause the video, graph this, find one 0 that's definitely an integer. So if you did that, you would have graphed this and found that this function, as a function, crossed the x-axis at -1. So if it crossed the x-axis at -1, that means x plus 1 is definitely a factor of that. If x plus 1 is definitely a factor of that, then that means I can use synthetic division to factor out that 0 of -1 from this polynomial, and then hopefully it will be something that we can factor on our own. So we're going to use synthetic division just like we have learned in the past. And we're going to bring down the 8. And continue this process. It's definitely, we know that it's a factor for sure because we tested it with the calculator. So if you get anything other than 0 as a remainder, you know you've made a mistake. So that leaves us with our new polynomial to factor 8x squared plus 14x minus 15. Now I can continue factoring this. So at this point you would multiply 8 and 15 together, get 120, and you're looking for factors of 120 that combine to 14. So go ahead and pause the video and finish this up on your own. Okay, so we found that -120 has the factors 20 and -6 that combine to 14. So then I split 14 up into 20 minus 6, 14x, 20x minus 6x. Then I factored by grouping, And then I got this factorization. Now, the important thing to remember is the big picture. This is just the factorization of that, which was the remaining factor when I had already factored x plus 1 out. So the complete factorization of this is x plus 1 times those two factors. So this is the complete prime factorization. If you're wondering why I'm not doing more difference of squares, that's because this is a sum, x plus 1, that's completely prime. Can't factor that anymore. This is also a sum. I cannot factor anything else out here over the reals. But here, you'd think that since that's difference, I could do difference of squares, but x is not a square. If this was x squared, we would do one more step, but it's just 4x, and I cannot continue factoring that over the reals, so we're finished.